Hello everybody and welcome to the ice-breaking of the class Advanced Hydrosystems Engineering for the students of the first year of Civil Engineering. In the following we will see together some fundamentals of hydraulics that will help you to better understand the related arguments for the class of Advanced Hydrosystem Engineering. In particular, we'll focus on Bernoulli's theorem applied to flow, uniform and permanent flow in pressurized pipes, pressurized water pipe with pump, hydraulic pipeline systems, and finally, free surface flows. Here you find a very good reference book for this class, in particular to follow the topics that we will see, and it's Fluid Mechanics Fundamentals and Applications by Cengel and Simbala for the edition of 2013. Also, here's my contact. I'm Giada Felisa. I'm a research fellow at the University of Bologna GCAM Hydraulics. Here you find my office number. And if you have any further questions about the topics that we will see in the next, you can also contact me at my email, which is giada.felisa2@unibo.it. So, if you have any doubts about what we will see in the following, please don't hesitate to ask me. Let's start with the first topic of this class, which is Bernoulli's theorem applied to flow. In particular, we will see the definition of mass and volumetric discharge, the definition of the coefficient of Coriolis, which is a correction coefficient, Venturi meter, and the extension of Bernoulli's theorem to real fluid and in real situations. Let's start with the definition of flow and mass discharge. So, in most cases, fluids move following trajectories, and these trajectories can be considered substantially parallel. If the motion of your fluid is only in one direction, if the fluid is said to be as a flow. So, our aim is just to describe this flow, and the flow is completely identified by its mass discharge, density, and the area of the cross-section, if these are known functions of space and time. Let's start with the definition of mass discharge Qm. So the mass discharge is the amount of mass that passes for a given surface in the unit time. So, for example, consider a generic section. Here you have a pipe where inside there's a flow. The flow is described also, of course, as we said, by its velocity, and we can see that inside the pipe the velocity is maximum in proximity of the axis of the pipe and its minimum near the walls. So basically we choose a generic section, but if we take a generic section without considering its inclination, when we define the mass discharge, we will only take into account the normal velocity to a generic section. So basically, of the entire vector velocity, we will take only its normal component. Hence, the mass discharge is defined as the integral on the generic section of dQm, which is again the integral on the generic section of the density of the flow, ρ, the velocity, the normal velocity of the flow to the generic section, and finally the infinitesimal area. In the particular case, which is one of the most common one, usually one takes the transversal section, which is a section where each point of the section is perpendicular to the vector velocity. Hence, the mass discharge can be described by the integral over the transversal section of the density of the flow, the velocity, which is not only the normal one anymore, but it's the entire component of the vector velocity, times the infinitesimal area. Generally, the density and the velocity vary in space and time, but in practical, the density can be considered as a constant and the velocity as approximate by its average value v, capital V. And capital V, the average value, is defined as 1 over a times the integral over the cross-section of the velocity times the infinitesimal area. This condition, which is the definition of the average velocity, plus the fact that we are considering a density which is constant, gives you the definition of mass discharge for incompressible fluid and considering its average velocity. So in this situation, in most practical case, the mass discharge is defined as the product of the density of the fluid times its average velocity times again the cross-section area, which is the transversal section. Let's consider now a fluid which is incompressible. So, in the case that we are in front of a incompressible fluid, which means that its density is constant, this fluid is defined only by its volumetric discharge, or average velocity, and the area of the section. So it's necessary to define the volumetric discharge, capital Q, which is the volume of fluid that passes through a surface in the unit time. Again, for a generic section, when we define the volumetric discharge, we have only the normal component of the vector velocity times the infinitesimal area, while in the particular case of the transversal section, the most common one, we are considering the entire velocity, which is the average velocity, times the infinitesimal area that, integrated over the transversal section, gives you the total entire area. Let's define right now what is a linear flow or gradually varied flow. Along the normal to a curve, the hydraulic head, which is defined as the sum of the geodetic height plus pressure height related to the pressure in a point over the specific weight of your fluid, it changes and decreases along its direction if the velocity and the curvature, 1 over r, which r is the ray of the curvature, increases. So when the rays of curvatures of the individual trajectories are really big, which means that the curvature is almost equal to 0, the variation of the piezometric head along the normal is really small and it can be neglected. So, the distribution of pressure, in this case, in each transversal section of flow is hydrostatic. It follows that a linear flow is a flow where you can consider that along its transversal section the distribution of pressure is hydrostatic, which means that your pressure follows the Stevin's law. Let's consider in a while a tank where you have a fluid which is in quiet. Then you have right here your free surface, and you know from Stevin's law that the pressure under a gravitational field increases with the depth according to the specific weight of your fluid. Right here on your right you see the scheme where you have a flow, so you have a fluid that is moving, it's not in quiet anymore, and in this case your trajectories are almost linear, which means that the curvature of your trajectories is almost equal to 0, and again it's valid this condition So in this particular situation, which is usually what happens when you study this kind of problem, you have that the hydrostatic pressure again the pressure follow a distribution again that is hydrostatic. Let's consider right now Bernoulli's theorem. A little reminder. When you study Bernoulli's theorem, of course, you have to take some assumptions, and these assumptions are that you are considering a gravitational field with ideal fluid, so it means that you don't have any energy losses. Your fluid is incompressible, which means that the density is almost constant. And also another very strong but useful assumption is that you are considering permanent flow, which means that the dependency of time is equal to 0. The Bernoulli's theorem is valid along its trajectories, which means that in this first consideration that we are making, we are seeing the flow as moving along only one trajectory, but of course there are lots of trajectories. So Bernoulli says basically that moving from point A to point B to point C under these assumptions, the total head remains constant. The total head is defined by this energy line, and basically it's the sum of three terms. That is the geodetic height, which is basically the ratio among the potential energy of the fluid over its weight, plus P over gamma is the pressure over the specific weight of the fluid, which is a pressure height, and these first two terms give you what is called the piezometric head. So basically, from these two terms you can define your piezometric line like the sum of exactly these two terms. Then you have this term right here, which is v to the power of 2 over 2g, which is the kinetic height, and it's given by the ratio among the kinetic power of the fluid, which is related to the velocity of the fluid, over 2 times g, the acceleration, the gravity acceleration. This terms comes from this terms is given by the ratio exactly by the kinetic power over the weight of the fluid, and from this ratio you obtain this term. And everything is equal to a constant under this assumption, which means that the sum of these three terms is constant moving from point A, B, C, but of course the different terms can be not equal from a point to another. This is true if we are considering the fluid which is flowing from along a trajectory. Now our aim is to move from a trajectory to a finite surface. So basically we want to pass from a local expression to an integrated one on a finite surface. To do this, usually one refers to average values of the local variable, and this is good if the global quantity depends on a linear function of the local one. But if it's not, and this is the case of the total head, because remember the total head depends on the power, on the velocity to the power of 2, then assuming average values leads to some errors. And to take this into account, usually one consider what is called the Coriolis coefficient alpha, or correction coefficient. Alright, so let's start defining what is the Coriolis coefficient. So Consider right now a transversal section of a linear flow. So we want to define the kinetic power. Right here we have that the kinetic power is defined as the integral of v to the power of 2 over 2 times the qm, where the qm is exactly the mass discharge that we have defined before, so it's rho, the velocity, times the a. Alright, then we can express this term in this one. 1 over 2 is bringing outside the integral, and this is what remains inside the integral. Hence, the Coriolis coefficient is defined exactly as the kinetic power integrated on a finite surface, the cross-section A, over the average values. So the average density of your fluid times the average velocity to the power of 3 of your fluid times the cross-section. Since the density is almost equal to the average value of the density, it can be neglected, so they are erased, and this is the final expression of your Coriolis coefficient. Let's consider right now a stream tube. So basically we are considering a little tube inside your greater flow, and this stream tube is defined by an infinitesimal area and the velocity that crosses this area. So considering this stream tube, we add that the infinitesimal power associated with your flow is given by rho g times h dq, and this can be expressed as, recalling Bernoulli's theorem, rho g times inside the branches is exactly your total head h, and dq is the volumetric discharge, so it's the velocity times the infinitesimal area. Hence, along each stream tube, one assumes that Bernoulli is valid, which means that the total head remains constant, the density is constant, which means that your fluid is incompressible, and again the continuity equation is valid, so the volumetric discharge remains constant. Under this assumption, your total power associated with your stream tube, the dp associated with the stream tube, and hence the total power remains constant. So the power P of an ideal incompressible fluid flow in permanent commotion condition is constant, which means that it assumes the same value on all the subsequent cross-section. What happens if the flow is linear? If the flow is linear, which means that Z plus P over gamma is a constant, so the hydraulic head remains constant as we have defined before, then you can split the power in these two terms. The first one is the specific weight times the integrals over the cross-section that multiplies Z plus P over gamma that multiplies VdA. VdA was the volumetric discharge. Plus, so we have right now splitted this term. Plus, this term right here is another term again, and it's this one. And this is gamma, so the specific weight times, since it's constant, it can bring it outside, so it becomes Z plus P over gamma times Q, because the integral over the cross-section of VdA is the volumetric discharge, plus P sin, and P sin is exactly the kinetic power, so it's gamma alpha that multiplies the average velocity to the power of 2 over 2g times the volumetric discharge. In case of uniform turbulent flow, alpha assumes values between 1 over 0.1 0.06 or 1.08, usually one assumes it's equal to 1, while in uniform laminar flow this correction increases and it's almost equal to 2. Rearranging this expression, it is also possible to demonstrate that alpha is equal to this expression right here. Let's see why. So, we started to say that alpha was equal to rho v to the power of 3, the integral over the area of rho v to the power of 3 of dA over the average value of the density times the average velocity to the power of 3 times A, which again was equal to the integral over the area of v to the power of 3 dA over v to the power of 3 of A. So this was our starting point. Let's say that another way to express the Coriolis coefficient is exactly the one in the next slide. So basically, I can express this little velocity to the power of 3 as alpha is equal to alpha is equal to I can, for example, say that it's equal to, so it was rho, the density, I can bring it outside and it's become rho to the integral power times the integral over the area of v to the power of 3 can be seen as the average value of v to the power of 2, alright, times little v times the A over rho m, which again we said that rho m is almost equal to rho m that multiplies v to the power of 3 times A. Then if I, for example, multiplies right here times g and g, so if I have to multiply right here, I can divide it right there, so I will have rho g, the integral over the area of v to the power of 2 over g times v dA, and again it's rho g, the integral, that's not the integral, it's v to the power of 3 over g, again times A. Alright, so it becomes the specific weight, gamma, the integral over the area of v to the power of 2 over, if I multiply right here times 2g, and I remember that I have also to put 2 right here, so I will have v in dA over gamma v to the power of 3 over 2g A. We have almost done finally, so we'll have in the end exactly what is reported in our slide. So it's another way to express, I just rewrite it, it's the specific weight times the integral over the area of v to the power of 2 over 2g times v in the A over gamma v to the power of 3 over 2g times A. So this one is exactly equal to this other term. It's just a way to rearrange it. And in particular, this one derives from the cinetic power, so we can demonstrate that the cinetic power is exactly this first term, because the cinetic power is given by gamma alpha and v to the power of 2 over 2g times q. Alright, so basically